Good afternoon, everyone, and welcome to today's ECA Learning Zone webinar on arc fault detection devices, led by ECA Commercial Associate Scolmore Group. Our presenters today are Jake Green and Tim Benstead from the Scolmore Group. Welcome both. Today, Jake and Tim will outline the current requirements for arc fault detection and the key considerations for contractors. They'll also demonstrate their latest AFDD products from Scolmore Group. Today's webinar will include a Q&A. You should see a question mark button on your screen now. Do please make use of this at any point in today's presentation, and we'll try to answer as many of your questions as we can at the end. And finally, viewers are reminded that a full replay of today's webinar, as well as our entire ECA Learning Zone series, is available on ECA's YouTube channel. That's at youtube.com/ECA Live. And if you're an ECA member, do remember to log in to the technical area of our website, where you can access our industry-leading technical support, including guidance notes, editable certificates, FAQs, and exclusive access to our technical helpline. Just go to eca.co.uk/technical to find out more there. And that's enough from me. So over to Jake for today's presentation.
Thank you very much, Omar. Thank you very much. Thank you, everybody, for joining us today. We do really appreciate your time. And, you know, arc fault detection devices, they're a topic that's been heavily debated over the last couple of years with the DPC coming out and with the amendments that we're seeing currently. Now, myself and Tim, you know, we've done this talk a number of times across the country, so apologies if you have already seen it. But we will hopefully today enlighten you into really how the standards have developed and the actual product itself. It's really a two-pronged attack when it comes to standards and the product itself. So, as I said, Jake Green here from the Scolmore Group and Tim Benstead, who is working for Scolmore Group as well. So what is an ARC then, Tim? Come on, what is an AFDD? Tell everybody.
Yeah. It's always one of those things doing a presentation when two people are in two different rooms. Well, we know that an AFDD is an arc fault detection device. It mitigates the risk of fire in final circuits within a fixed installation due to the effect of an arc fault. The standard that deals with it is BSEN 62606. It's been a standard that has, in effect, Jake, remained unchanged, but then it's not a very old standard, probably around about 2013, something like that. And so the checks and tests associated with an AFDD are very much locked into AC, final circuits, and so on. And they reduce the risk of fire by ignition under certain arc fault conditions. It's an electronic device, though. It's monitoring the nature of signals within circuits, and it interacts with the means of circuit protection in that sense, rather than actually measuring a physical or monitoring an actual physical event, such an overload affecting a magnetic field or a resistive element there. So sort of quite different, but in effect, that's what an AFDD is.
So necessarily you couldn't really have them, Tim. Just, I know you mentioned there that they work in conjunction with another device. They couldn't operate on their own then, so they couldn't be a standalone unit. Now, I mean, some contractors and some people have had a conversation with us where they've said, well, why don't you use it the same way that you use an RCCB and group it together and look at a bank of circuits?
I suppose in some ways you could, as long as you then doubled them up with a circuit breaker that was related to it. And so, of course, in the early days, an AFDD was effectively bolted onto a circuit breaker because it required access to the means of break of the circuit. And that manufacturers, not just Scolmore, but across the board now, manufacturers are going, well, hang on a minute. We can now start to combine the advantages of an AFDD with a circuit breaker with an RCD, and we have the combined RCBO with AFDD arrangement, and that much more sensible way of operating. It limits the amount of space taken up within a consumer unit. It has so many advantages, and of course it's a one-stop shop that allows that work to be done.
Yeah, I think when I know Omar mentioned that we were going to talk a little bit about our product, but here at the Scolmore Group, we only do a arc fault detection device with an RCBO. Now, the reasons that we've chosen to do that is primarily because of our offering in the marketplace. It's not mature enough, let's put it that way. I think that's a polite way, in the sense that it's not mature enough, it's been around long enough to include an arc fault with an MCB. When you think about the other manufacturers that are out there, they've been around a long time producing circuit breakers, that's the word I'm looking for, circuit breakers for a number of years. So it's prudent of those to actually sit there and think about using it for a retrospective solution, as it were. So how does an arc fault detection device work then? Well, again, we can only speak on behalf of what we do here at the Scolmore Group. As you know, there's many other manufacturers out there that are looking at arc fault detection devices. We look for 3 parameters within ours. So we look for a high frequency radiation characteristics, can be detected due to the carbonisation in the path. We look for a specific waveform as well. Now, when we look for the waveform that we're looking for, is probably that's something that's not been programmed into the device. So it's a microprocessor that sits there with a number of signature arcs on the system, and ones that we're looking for are currently programmed into that as well. And then the third one, I've just jumped a gun there, Tim. Is the time and the duration that we're seeing. So if it's happening for a long period of time, it's not a waveform that is typically seen within the device, and there's a number of or a higher limits on the current, then we would see the devices sort of operate from there.
Yeah, the other bit tied into that, of course, is what's called the current waveform periodic integral characteristics, and the issue is when you're dealing with arcs, it is inherently complicated. This is not straightforward stuff, and it requires manufacturers to analyze what is the difference between a normal happy arc that you would normally generate just because you're switching a light on, and it may have a wee bit of inductance associated with switching it on and off, or that you've got a drill that you've plugged into the normal mains and it's got some sparking and arcing. These are normal arcs. They're a happy function of the usefulness of the bit of kit that you're actually working with. The issue then is, how do you differentiate that from an arc within a conductor that's making a poor connection, or that's got a little bit of a break in it but not much? It's that nuance where manufacturers are having to do the work to make sure that, yes, this is truly an arc. And so what they do is, rather than looking at one thing, as you rightly say, they look at multiple factors and go, actually, we need to have that and that and that. Only when all those appear do we say that this is an arc that we don't want. It's an unwanted arc that needs to actually operate a protective device.
Yeah, I think if we go back to the point I was making a minute ago, where we start doubling them up and using them as an RCCB, we imagine we've got a split load board and we've got one on the front end. If we've got one of those signatures on various different circuits, you could see an unwanted tripping or an unwanted operation of these devices happening, and hence the reason why they need to be singular when it comes to individual circuits.
And of course, Jake, if you sort of stay here, in terms of the standard of 62606 actually details the type of plugged-in device that actually you have to monitor against. So you've got a vacuum cleaner rated at a certain current rating. You've got switch mode power supplies, capacitor start motor, electronic lamp dimmer, fluorescent lamps, halogen. There's a whole range of bits of equipment that generate arcs of a certain characteristic that manufacturers measure against, and they are within 62606.
Yeah, I'm just thinking sort of out loud here when it comes to that then, Tim. So what the standard is calling for is for a group of certain products to be included. So if there was some developments work that was going on with, let's say, I'm not switch mode power supplies, if there was some development that was going on around that, the ARCs would see it as a whole and not individual products as such.
Typically, it would have to be taken that way. Yes, I think that's a reasonable assumption there. Obviously, there could always be something that currently isn't out there that may suddenly surprise all of us in terms of the shape of the ARC and the signature that it provides. But at the moment, it sort of does sit within that scope. And interestingly, of course, that standard 62606 hasn't changed in 10 years, or you know, so it's been pretty stable as a standard, and that's with a new product. So it's interesting that it seems to have got it sort of right.
Yeah.
I mean, it's one of these things that standards always develop, we know that, but it's stayed relatively stable.
Okay. So what is electrical arc then? An electrical breakdown of gas that's produced prolonged discharge between two means of conduction. So if we've got a slight gap there, we're seeing that there's a high resistance joint and it's trying to break or
yeah,
that gap between there.
That's it. It can happen in air. Obviously, with this, depends on the voltage rating that's there. We know it breaks down in air because we see a lightning stroke. A lightning stroke is an electrical arc. It's a very big one, and you need massive voltage and current for it to occur. But it is true in a cable. It's obviously at much smaller voltages and so on. But once you've got a gap, once you've got some dielectric, something for the arc to pass through. Can be air, but typically it would be some carbon material. It would be something where there's that creation of that high resistance joint. Then you'll get an arc.
Now then, what is the primary causing of arcing then, Tim?
Generally, Jake, arcing occurs where there is relative movement between two positions, two joints. So it can be, as I said already, it can be caused by a small break in a conductor. You know, the movement is slightly apart and it draws an arc as current is flowing. And typically that would be the way that it would occur. You can get series arc, parallel arc, but it is this relative movement between the 2 points that permits an arc to not only be drawn, but to then be sustained.
Yeah, just going back to that series arc then, Tim, and the parallel arc. So are you suggesting that actually you imagine you've got two cables that if there's a short enough gap between them, it would jump sideways, even if they were not the same conductor?
Yeah, absolutely. That could be the case. I suppose the bit that sort of sits in there though is in a parallel arc. If it was jumping sideways, you would probably, in most instances, get to the point where it's almost treated like a short circuit for the circuit breaker to operate, and it would probably operate before the arc fault element would operate, simply because with a parallel arc, it tends to drive that, whereas with a series arc, the circuit breaker just sees current flow, and so it's probably in that area. But absolutely, parallel arcing does occur, and obviously, if the current is low enough, the circuit breaker won't see it. It just sees it as an additional load, as it were.
Yeah, I think we'll come on to the current of these in a second. But before we do, what is necessary then to generate an arc? We can see there is, as we mentioned, it's that gap between there. And once we see that gap, that's where we start to see the carbonisation happen with PVC cables. Now we know that there's been some talk around other conductors may not build this carbon up, etc., or other cables may not actually build this carbon up, but we haven't seen anything as such yet where it's suggesting that using certain types of cable it would mitigate against these arcs that we're seeing. So really, it's a build up, isn't it, Tim, of carbon.
Yeah.
Once that carbon exists, that's when we can sort of see this arc happening and really creating these fires, as we can see on screen here.
Yeah. I mean, typically it does require a material for its pass through, simply just to generate the heat. That's absolutely the case. Although it is interesting, we have come across instances, haven't we, Jake, where somebody's plugged something in and it actually has taken out the AFDD, and of course we have no control within the fixed installation over what somebody plugs in, and so there's an element there that AFDDs are clearly working, they're doing their job, but when you then come to the consequences of arcing, they can be ferocious. I mean, what we see on the right hand side is an arc fault. Now, you know, we use sort of license in the sense that this is not a single phase arrangement, but arcing is arcing, and it generates vast amounts of heat.
Speaking of heat, I'll let you take this one, mate.
I have no idea. Anyway, no. Okay. This is an odd little graph, and you may think, well, hang on a minute, that doesn't look right. But if you actually look with fine detail on this graph, you'll see that while it's a sinusoidal type waveform, it is not as you might normally see it. What we're seeing here is the effective heating effect of while an arc is in existence at a particular point. So a high temperature at the fault location, they can cause the path of the carbonized material to vaporize. So you haven't just got a piece of carbon there. This is now turned sort of slightly gaseous, and the arc is now passing through air through a material that is sort of just floating around in this very tiny space, and heat is being generated. And the sort of waveform that would be created is not too dissimilar to this. And of course, our AFDD now is seeing this type of arrangement, or part of it is seeing this. It's looking for other things as well. And before it even becomes a problem, it would take out the circuit. But yes, no, this is a graph or a waveform of a particular arc under the heating effect of the I²R power losses.
You don't stare at it for too long because it might hurt your eyes.
Yeah, it needs stretching out a wee bit.
It does. Now, this is probably one of the big things that we wanted to sort of get across to you. Now, it'd be very easy for me to sit here and myself and Tim to sit here and suggest that actually, when it comes to arc fault detection devices, put them everywhere. You know, they're great. They're going to mitigate against the risk of fire. But we're seeing, you know, certain people put on specifications. It must be full arc fault detection device, and we're kind of sitting there going, okay, we hear you. You know, we're not suggesting that that's wrong or that you need to have a think about what you're doing. However, this particular chart that we see on the screen here is talking about how fast an AFD should disconnect when it comes to current. So we've mentioned about the other two parameters. This is the third one when it comes to how much current there is needed for the last parameter to be seen. So we can see on the top there that we've got 2.5 amps right the way up to 63 amps. Notice that we don't have anything less than 2.5 amps. Now the standard, that 62606 standard that Tim has been mentioning, calls for there to be a 2.5 amp current on this parameter. So it's suggesting that actually 1 second is the time there, right the way through up until that 63 amp, and it's going all the way down to 0.12. So Tim, what's happening to the 1.5s and the 1 amps of the world of the lighting circuits that we would typically see?
I think at those low current levels, Jake, the problem arises that there is, whilst it may be possible, highly unlikely, but whilst it may be theoretically possible to create an arc and sustain it, the amount of energy generated by such a fault is unlikely to be able to cause a fire. And of course, Chapter 42 is to do with thermal effects and fire and the concerns that we have with that. So when we look at the standard here, and this is just a table taken out of the standard, and these are the test arc currents that they're looking for. So they will set up the test rig to generate this current, and they're saying there's a maximum break time of 1 second. So at 2.5 amps, you're allowed to have a second. And this is a graph on a slope. You can see, because of course by the time you hit the 16 amp and 32 amp and the 63, you're getting very little change in the maximum break times. They're sort of fairly much flattening out, so it doesn't much matter where you go to, it's going to be at about 0.12. So at the low currents, you can permit quite happily an arc to exist for a second, which seems to be an awful long time. But as you get up in values of current, then of course you get a very rapid increase in temperature, and you must therefore get a much more rapid reduction in the break time that's permitted for the device, for the manufacturer to make sure that they're getting their device in line with the standard. It is to do with an I²T arrangement where you're looking at the amount of current and time and looking to see the heat that's generated during that period.
So we're not suggesting that when it comes to putting every device on arc fault detection devices that they are that's not right. However, what we're suggesting is that if you had something, you know, let's just talk about a single dwelling unit and said it was a 3-bed semi-detached house, you'll probably look at that and go, right, okay, well, if I've got an upstairs lighting circuit and a downstairs lighting circuit, what are they typically drawing? And you would probably say, I don't know, 50, 60 watts maybe, if it's a smallish house.
If it's an older house. Yeah, more modern properties will have LEDs, they'll be drawing much less.
So you're just simply not going to have the current there to trigger this parameter. Now, if you're working in somewhere like where I am now in an office, you know, you may be sitting there thinking it's got merit, it's got benefit of being on there. It's going to be that test current. We're going to see an operational change when it comes to a 6 amp device. Excuse me. So Tim, when we sort of think about a shower circuit, then are we suggesting that there's probably too much energy and it's going to operate too quickly?
I suppose the issue around once you get to values exceeding the 30 amps or so, you've almost got to the point where shall we say the fire's already happening. It's happening so rapidly because you're dealing with so much current in a series arc that struggle to measure it has already happened before it's thought of saying, is this a dodgy arc? So it becomes problematic. I think it's so at very low values of current, it's probably worthwhile moving on to the next slide, Jake. But at very low values, there's hardly enough energy to drive fire, and at very high values there's so much energy, fire's already taken over. But once we've got into this mid ground, hence the regulatory requirement around socket outlets, then we can do something about it, and AFDDs work very well.
Yeah, so the types of faults that they're looking at then, as we've already mentioned, is in one single conductor. We're not necessarily just looking at the parallels now. This is something that we've not seen before when it comes to looking at faults. So it's one single conductor. Probably prudent to mention about ring final circuits at this point, suggesting that actually you can't get the fault that is needed or that high resistance joint to generate a series arc when it comes to ring final circuit. So we've just mentioned a little bit about where, you know, we're looking at socket outlets when it comes to this. Typically speaking, everybody uses ring final circuits, but you can't actually get the fault that is needed under the high resistance joint to generate a series arc fault. It will choose the path of least resistance, it'll go back around the other way. However, when you are starting to plug things back into that circuit, doesn't matter what socket outlet it is, it does then become that series or that serial fault again. So that cord that we see coming off of the flex, that would then generate that series arc.
Yeah.
So
yeah, that would be protected by the AFDD. Yeah.
Yeah. So do they work on ring final circuits? Well, you can't actually get that fault on the circuit. Therefore, the things that are being plugged into it, yes, you can get that series arc. We can see
and of
there.
course, it will work on the parallel part of it, Jake.
Indeed.
As we come to it.
There you go. I've switched it for you.
I know. Well done.
So yes, they still will operate on the parallel arc side. Now, if you are using the RCBO setup with an arc fault detection device, which is, as we've mentioned, that we do, the likelihood is that the actual RCBO side of it will see it quicker than the arc fault detection device will, just by its very nature.
Certainly, if it's to earth, it will. Obviously, if it's line neutral, the RCBO won't see it. But the circuit breaker part of the overcurrent element might see it. But yes, that's absolutely the case. Yeah.
Now, when it comes to the fault check sequence, some of you may have seen the device back a few slides. You can see that it's got a little indicator there, and that indicator is set up for telling you what types of faults exist within that arc fault detection device. It is the same button that you press to test the RCBO side of the device, but you will see a sequence, as you can see on the screen here now. So it does cover that series arc fault, the parallel arc fault. You notice that it's got an over voltage fault on there as well, which I'll come on to in a second. You've got self-test fault, and then you've got no fault. Now, within the standard, it does call for it to have a self-test function. Believe, Tim, it's once a day that it needs to test itself within and under that 62606 standard. So it will go through a self-test once a day at least, and some manufacturers may make it more of a cycle. But in terms of what you guys need to do as a test when you're out there on the road, going around doing an EICR, or you're going to fault find on there, there isn't actually a test instrument for it within the standard that is needed to actually be used. Now, there are instruments out there that can test it. However, you probably either won't want to carry it around or wouldn't actually like to try and generate this arc that is needed. I'll just go back to the over voltage fault. Now, we know that we're using SPDs now. There's been lots of questions around that, from many moons about SPDs. But today, looking at arc fault detection devices, over voltage fault, that's looking at something similar to an SPD. However, it doesn't actually deal with the issue that's at large. It just simply operates. So if it sees over 275 volts, it will operate itself. So it will tell the microprocessor, will say, okay, I've seen 275 volts now. I need to do something about it and I need to operate. But what it doesn't do is it doesn't dump the current down to earth. You still need that SPD within the system in order for it to dump it down to earth. So yes, it will tell you if it's gone out over that 275 volt threshold, but it won't do anything with the current that's sitting there.
And it's every manufacturer's check sequence will be different in all likelihood. This is ours. I think that's worth saying. But you're right. There would be no test instrument you could use. The bottom line is you're still looking at an electronic chip sat inside a device monitoring signals.
Just on that chip itself there, Tim, I mean, as a manufacturer, we obviously look at what other people are doing, and we believe that actually a lot of people will use the same chipset because they're independent chip manufacturers. Now, so you may see some of the manufacturers and they may say, our sequence is exactly the same as that. Some may have something different, and that's because they're using a different chip in there and what have you. But just in terms of the regulations, then, Tim, we are comfortable now with the position, no?
We are thrilled with the position. This was a long debated regulation. Folks that have joined us will remember that the use of AFDDs was recommended. Obviously, this is not a UK regulatory number. This is an IEC stroke Senelec. It's come down to as a standard number. The UK's position is in one sense different to that which occurs in the harmonised document that came down, but it is, I think, internally consistent. I think that's the position. We actually recognise that AFDDs have a use. They're very useful for final circuits, and they're very useful in those areas where you've got increased risk. And after an awful lot of debate and discussion over a good period prior to Amendment 2, we actually did come to a consensus, and what we currently have is a consensus position, and obviously unlikely to change until any further amendment. But I don't. This is personal view. I don't think it will change, but that's not to say it can't. I think the one tweak that may occur, if you look there at 6 stories, that's probably going to change to 7 stories, simply because the laws change slightly, and we've got a note in the regulation that says we sort of recognise that the law might change, and so we may need to tweak things. But the 18 metres is still there, and it'll probably drift to 7 stories. But I don't think we'll need to do anything until the next amendment on that for clarification. But yeah, all of those areas are increased risk, Jane.
Indeed, they are. Yeah. Now we start to think about the tragedy that happened at Grenfell. That's got to be the direction of travel for the committees when they're looking at it, saying, right, okay, well, there's a higher risk area. We don't want to see anything like that happen again. Therefore, that's a valid point of having that one in there. You've got houses of multiple occupancy. Again, the homeowner, the person that owns that house, that is subletting it, let's call it, for the want of a better word, they have no control of what's being plugged into the system. Therefore, it adds that extra level of protection. Student accommodation or purpose-built student accommodation, we can see on the screen there. You bet if you've got kids that have got that are students, or once a student myself, if I need to charge my phone and there's one lead that's damaged in the house, you bet I'm still using it to charge my phone. Likewise with students, so we can see why that one that is in there as well. Care homes, again, licensed care homes. Again, people will be, if there's sort of some issues, they may not know how to sort of get out of the property. So if we can mitigate against the risk of fire within there, then again, why would we not? Notice though that we've mentioned it a little bit, that the fact that it is those socket outlets only. Going back to our shower circuit situation, Tim, it's probably fair of me to say that actually, once an electrician has been in and installed a shower circuit, the person that's using it on the end doesn't really have much interaction with them. They have no way of changing that circuit. Therefore, the people that are going in are competent. They've gone through their certification, or their CPS. That's the word I'm looking for. The CPS, to make sure that they are fit for, or competent. Let's say competent. So they're competent.
We would hope so anyway.
Yeah. We certainly do, but yeah, so if they're competent, there's no way that the person that's using that system has any interaction with it other than pressing the button to turn it on and off, or maybe the pull cord. Now, when it comes to the socket outlets, like the regulations suggest there, we can't control any of that. We don't know what people are going to be plugging into the system. I think it's right of us to say that it's probably sitting there as a fair judgment when it comes to installing arc fault detection devices. Yeah, makes eminent good sense, I think. The second recommendation. We still have a recommendation. AFDDs work, and so why not include them if you can? So it might be that in a domestic setting, that's a normal domestic, for example, that the use of an AFDD makes good sense. You're not required, but we do know that in terms of the guidance within 7671, recommended is you ought to do it. You should do it unless there's a good reason not to. And so
I think if I was having my consumer unit replaced, I would be sticking an AFDD in my house. That just makes good sense for me. Yes, there's some small additional, or there's an element of additional cost, but it makes good safety sense, and I would just include it as a default position, speaking personally.
You've got to convince a lot of people.
I know that, but then I'm old enough, Jake, to remember when RCDs were first introduced, and they came in as a recommendation, and they were then required to supply a socket if you were going to supply equipment used out of doors, and then they were required for the more and more, and now they're mandated. I mean, just everywhere, you know, and even on lighting circuits. So in domestic premises. So the use of RCD started as a recommendation a lot of years ago, and developed over time because they recognised they actually work. I mean, we might still go, well, it seems a bit excessive, but you know, that I'm not saying that I think at personal level, I'm not saying I think AFDD should expand more and more, but I can understand the common sense, the good sense of mandating them for those specific locations and recommending it elsewhere.
Yeah, I think.
And there are exclusions, aren't there? You know, in medical locations, for example.
Yeah. And why would we not want to install something that's going to mitigate against fire? It's another level of protection. We've got SPDs, we've got RCDs, we've got MCBs, and now we've got art fault detection devices. We're seeing that it's almost like a complete circle now. There's no way to go for any faults, and we're preventing against them. Just some of the other bits to mention on the bottom there. Make sure that they're being installed at the origin of the final circuit, and it's not exceeding that 230 volts AC in single phase circuits. Interestingly, we haven't seen anything, or we certainly haven't developed anything yet when it comes to a 3-phase setup when it comes to art fault. So there is some sort of development work that will go on, I would imagine, and it won't be long before somebody comes up with something like that.
Well, I think we'll see how the future develops, isn't it?
Anything you want to add just on the conclusion side?
I think we've pretty much covered it. Like you said, Jake, we've got this rounded picture of RCDs, AFDDs, circuit breakers. We've got that level of protection that sits there, and it makes sense in the higher risk areas to include an AFDD. They work. So that would be my conclusion.
Perfect. Omar, is there any questions for us to take? Or has anybody got any questions they want to pose to us?
Thank you very much, Jake and Tim, for your presentation. Really comprehensive, really in-depth, fantastic stuff, as always. And Jake, yes, we do have a few questions from the audience.
I'll just go now, Jake.
I'll just bring those up now. Where are we? Here we go. So, first question for you guys. Can the client opt out of AFDDs in the same way as SPDs? And they say they're referring to regulation 421.1.7.
Yeah. Is this in a domestic setting? If the answer is yes, then yes, they can. There's no stopping them doing that. And even in, as you could do in other regulations, you could apply regulation 120, and I've forgotten the next bit of number, but you can sort of step outside of the requirement of the standard and record that. It's not necessarily wise to within those areas that are mandated, because the level of risk has suddenly risen, and should there be subsequently a fire and it's not, these devices have not been included, then there's a fundamental problem. But certainly within a domestic setting where it's a recommendation, they can indeed opt out. I personally wouldn't, but
yeah, I think just to add to that, Tim, we've been asked this question a number of times now, and this is just some of the thoughts that we've had, not necessarily a true opinion or anything like that, but Tim just mentioned stepping outside of the regulations. We've had a couple of people asking us, what if we've got cleaner sockets that have been locked? Can we admit against our ARC fault detection devices in a scenario like that? And as Tim's mentioned, yes, you could, and if you choose to step outside of BS 76711, then you need to have good imminent reasons to do so. You need to make sure that it's going to be no less safe in doing so. So if, for example, they said, right, we've got some cleaner sockets that are locked, all of the things that are being plugged into the system are being pat tested or port of appliance tested on a regular basis. The only people that have the keys to these are the cleaners, etc. You may want to do that, and you may choose to do that. However, it needs to be no less safe, and you need to make sure that you are, doing all that you can to make sure that it's going to be that no less safe.
Yeah, and you'd still need to record it on your EIC.
Okay, thanks, guys. Next question. Obviously, AFDDs are slightly more advanced pieces of tech. The question is, how often does the built-in firmware need updating, and how is it updated?
It isn't certainly the Scolmore product isn't updated. We do know that another manufacturer has a mechanism for updating the firmware. The firmware only really needs updating should there be an unknown ARC, and remember that's in a sense stepping outside of what's required by BSEN 62606, which has a specific list of products that you are testing against. And in a sense, until that standard gets updated and grows the list, the point of the firmware update sort of gets a wee bit lost, because compliance with the standard is what manufacturers would manufacture to.
Okay.
That makes sense.
Hopefully, if it doesn't make sense, hopefully we'll get another question in to expand on that. Next question: are there any issues with nuisance tripping?
We've had a few scenarios where we've had calls come into the technical helpline, and people have sat there and said, "It's your device is not working." Now, one way that we can sort of test that is to take all the things off of that circuit, whether that's an appliance, whether it's heaters, or whether it's tail rails, or bits and pieces like that. Strip everything off of the system, and then look for any unwanted tripping from there. If it doesn't continue to happen, then we sort of know it's the product. And we had someone, and they were arguing the point that it was our device, yet they took the appliance off the system and they didn't have any faults. They said it's a brand new system. Why is this operating? So and it actually turned out that it was the appliance. So can you get unwanted tripping, and can you maybe have something that's causing it to operate within the same sentence? Then absolutely yes. But just in terms of the unwanted tripping, generally speaking, no, it wouldn't happen.
But I would argue, Jake, the device is actually working. It may be unwanted, as is, it's a nuisance. But welcome to the world. You've got an ARC fault, and the device has actually found it. I think that's nearer the mark. I think there's certainly, I've heard anecdotally that when an ARC fault device is installed in a new installer, a full rewire, and what have you, happy days. The minute it's just added to an existing circuit, then occasionally that will then trip away. But it's because there's some fundamental underlying loose connections that are sitting there on the circuit and have sat there for a period. Now you might argue, well, if they've been sat there and they've not caused a problem so far, no biggie. But it's only no biggie until you draw sufficient current that it'll maintain the arc and then cause the fire. You're always dealing with risk, aren't you? We stick an RCD on all sorts of circuits because there's a risk associated with it. And in the same way, I think that's it. So Jay, you're absolutely right. But like I said, I wouldn't call it unwanted tripping. Simply the device is doing what it's designed to do.
Yeah.
Next question here: would upgrading or when upgrading or replacing a consumer unit, to existing circuits in an HMO, does that require AFDDs to be fitted to the socket outlet circuits?
Yes.
Yeah, I think
Nice and
that's
easy.
yeah. I think the issue is your new stuff has to conform to 7671 Amendment 2. Now you can say, well, the existing circuit didn't need it. We're not touching the existing circuit, and that's absolutely right. But you have fundamentally changed the parameters by updating the consumer unit, and I think Jake's absolutely right. I think yes, you should.
Okay. We've got another couple of questions here, and then we'll be looking to wrap up. Let me scroll down here. If there is no load current, can the AFDD detect series faults? If not, surely removing all loads will not be a diagnostic test.
Yeah, when there's no current flow, the AFDD won't operate in that sense. But if there is a series, if a small load is connected and a circuit is formed, then the AFDD would sense it. What I think Jake rightly was mentioning was that typically what we find, and it's the same when we're looking at checking for RCD nuisance operating, is you sort of say to people, well, turn that off and turn that off, and then turn things back on one at a time, and you sort of tend to find the thing that's actually caused the problem as you sort of do it. So it functions as a diagnostic test in a practical setting, I think.
1 sec.
And I think you've sort of answered. Have we set off
You set off Siri.
Siri? Yeah. I wasn't going to say the names of the other ones in case it sets off a load more in the audience, but. Tim, I think you answered the other question that we had on our list here, which was about how does one go about finding the actual faults and determining whether a trip has actually occurred. So
Yeah,
whether you want to expand on that a bit.
As we go through the sort of the sequence, I think these devices are great at telling you there's a problem, but actually pointing out exactly where the problem is probably a step too far. You know, if you've got a series arc, you go back to the old way of start splitting your circuit down in half and then half again, and sort of going from there. The same way that you would do any sort of fault finding.
Yeah.
I mean, it's going to be a little bit more difficult because you're going to have to start running out insulation resistance tests to work out exactly what piece of cable that there is a breakdown, etc. You could be there for some time when it comes to a series fault for sure, purely because you can't see inside the cable.
Yeah, no, you're absolutely right, Jake. That once you get past that, it's not a plugged-in appliance, then you're into the joy of splitting circuits down. Yeah.
Okay. And I think we'll wrap up there for today. Thanks once again to Jake and Tim for that excellent presentation. This presentation has been recorded, including the Q&A, and it will be available to watch back on ECA's YouTube channel. So that's youtube.com/ECA Live. And I would also like to mention once again the ECA member zone and the technical area of the ECA website, exclusively for members, where you can access all of our own material and guidance notes and FAQs on AFDDs, as well as Amendment 2, whole range of technical issues there. So thanks again both, and to our audience also for joining us today, and have a great afternoon.
Thank you very much.
Thanks everyone.